We are happy to have Professor Ashutosh Kotwal from Duke University telling us about high precision measurement of the W boson mass with the CDF II detector. So please begin.
Okay, thank you so much. It is very big honor for me, a pleasure to be here and tell you about this latest measurement from CDF on behalf of the CDF collaboration. So what you will see here, this is a picture of the CDF II detector, a little background. So CDF started as an experiment and collaboration in about 1983, 84. The first data taking, I think, happened in 87, maybe even 85 a little bit, but then 87, there was 4 inverse picobarns was collected. Then there was a run called Run 1, which was in 92 to 95. So both CDF and D0 collected data in the 92-95 period. So those measurements are called the Run 1 measurements. Then there was an upgrade to the experiment, both CDF and D0, and the energy of the Tevatron was also increased a little bit. So that run started, Run 2, as it's called, started in 99 or so, and physics data taking about 2001 to 2002. And then that ran till 2011. So the measurement presented here, which is from the CDF II detector, the upgraded detector, will be using all of the data from 2002 up to 2011. So about 9 years of data, the entire data set. Okay. So for this run, here is the new silicon detector up to a radius of about 30-35 centimeters. This silicon detector, very important for every other kinds of physics, top physics, B physics, of course, is not used at all here. Everything is anchoring on the drift chamber. So from about 40 centimeters to 1.3 meters, this is the main drift chamber. Outside is the electromagnetic calorimeter and hadronic calorimeter here. So the drift chamber will be something we will emphasize heavily. It is where all the momenta measurements for electrons and muons coming from, both direction and curvature, which is converted to transverse momentum. So you will see how important it is. And I'll emphasize that sort of the emphasis we have placed on getting the momenta fundamentally from the drift chamber, from both the calibration of the chamber itself and the magnetic field and so forth, the amount of energy loss in the experiment and all this. This is something we have done for 3 times now. Our first measurement was 2007, then the next one was 2012 from more and more data, and now using the full data set 10 years later. So this is something we emphasize because none of the other experiments have emphasized a fundamental understanding of the tracking chamber and extracting the momentum fundamentally from there. So we are able to measure the Z mass just like we can measure the W mass and use it as a proof in some sense that our momentum calibration is correct. Okay, so on this note, let's start with some detail. So a few words of motivation on standard model and possible new physics, but I will quickly go into the strategy of the analysis where this kind of robustness, which means we will try to make measurements of important quantities for the experiment in multiple ways and see if we get consistent answers. A few words on the experimental apparatus, but focusing mostly on the drift chamber and the electromagnetic calorimeter. Then I'll discuss how the simulation is done, how the distributions from which we will extract MW and many other quantities, how those distributions are simulated, and how the fitting is done from the simulation to the data in order to get all these quantities. Then discuss how the systematic uncertainties and are extracted and what are constraining them, give you some conclusions at the end. So this paper, you all know in science, has a 50-page or so supplemental section at the back. So most of the details are there. You will also see in the supplemental section that there are a lot of references to the previous 2 papers we have. So every time in 2008 and 2014, there was another Physical Review D long article in addition to the Physical Review letters. And many of the details I will present here, some of them have changed, so I will discuss the changes, but many of them are the same as the 2012 analysis, for example. And so many of those details are actually referenced in that paper. So really, we have tried to keep the 2 papers at least exclusive, which means really there's 100 pages of details at least on which the analysis is based. So with this, a few words on standard model. So we know the axioms in it. There is a lot of quantum field theory, special relativity, a lot of group theory is there. Gauge invariance is extremely important. And then there are some modeling aspects. So there are, in the electroweak sector, two couplings. You can call that the SU2 coupling and the hypercharge coupling. And then because of symmetry breaking by the Higgs field, there is a mass scale, the famous Higgs vacuum expectation value. So those three parameters alone can be extracted from mz, the muon decay constant G Fermi, and alpha electromagnetic. So with these three alone, you can have a tree-level description of the electroweak sector. Therefore, you can get a MW prediction at tree level without any quantum loops already from this. So next we go to loops involving top quark, then we get to loops involving Higgs bosons. So knowing the top quark and Higgs mass now pretty accurately, we are able to get these diagrams on the left-hand side also calculated. So I will show you the number on the next slide. Knowing this number quite accurately from theory now means, in some sense, the motivation of the MW measurement has changed. 25 years ago, before top quark was discovered, this diagram was used to infer what MTOP might be. Afterwards, LHC has measured top quark precisely. Tevatron discovered in 95. Now Higgs boson became the target in the early 2000s. After that discovery, and now the Higgs boson mass is also known, then MW motivation changes and in some sense becomes more interesting, because if there is some new physics and new quantum corrections, maybe we get some sensitivity to that. So this is the number that comes from the theorists, 8357, 4 MeV uncertainty from mostly M top, then MZ also 2 MeV about from MZ, some contribution from alpha electromagnetic. The Higgs uncertainty is actually very small now. Higgs mass is very precise. The calculation itself in electroweak theory is exact. Two loops, some theorists told me. 3 loop contributions are also included. Some 4 loop contributions are also included. So the missing 3 loop, 4 loop, and so on, and higher order loops, the estimate from the missing loops and missing higher order corrections is the other 4 MeV. So it's quite nice that the parametric uncertainty and the intrinsic theoretical perturbative uncertainty is about the same. So both are quite small. We had a few words in the paper on new physics possibilities only as a way of introduction. It's of course up to the theory community to see if what new physics model might fit this particular answer. So here is just a short list of things we briefly mentioned in the paper. So one of them, just to illustrate, is this one. Some people find it attractive that you can add to the standard model in the Higgs part of the standard model just one additional field, and this field can be very simple. No standard model charges at all. So it's some kind of dark Higgs-like extension of the sector. But because it is also a scalar, it mixes with the Higgs boson. And because of that, the other standard model particles can feel the effect of this extension. So that is calculated here for different masses of this additional scalar. It could be light or could be heavy. You get contributions to MW as a function of the mixing angle. So the simplicity of this is the reason I sort of picked this plot, just to illustrate that it has only 2 parameters, the mass of the second scalar, and alpha is the mixing angle between that scalar and the Higgs boson that we know. Now, this variation itself, if you put in other constraints from other precision measurements or rare decays or something like this, then this number may become smaller, but this is what this particular paper illustrated. Okay, then the other favorite, supersymmetry. In the older days, more larger corrections were possible because of loops from supersymmetric quarks, but now there is significant exclusion from the LHC. So we sometimes get asked, your plot can be modified, but the question to the theorists, whoever makes these plots, it turns out it is not such an easy answer, because the parameter space of supersymmetry breaking can be quite large depending on what specific model is used. So, putting the exclusions from the LHC into that parameter space, turns out maybe is not so easy. So, but people say maybe a few MeV, tens of MeV is still possible, even from supersymmetry. Okay. So as a way of motivating MW for run 2, if we look at the documents from 95, 96, which were presented as a way to motivate the Tevatron run 2, the entire 10-year running. Then in the precision sector, it was recognized that mTOP, measuring the top quark mass, would be important. It was recognized that measuring MW would be important. So the entire run 1 measurements from the 92, 95 data, they were not yet ready by 98. Those were published, some in 98. I was working on it, and those were published in the 2001. And at the same time, the LEP measurements came out in 2001, 2004. Final publications were in something like 2005, 2008. But some information was available. So this blue ellipse is the situation at the beginning of run 2. So the motivational statements there was, if we can get an MW measurement of something like 40 MeV, 40, so maybe an ellipse, something like this, that would be quite a success for run 2. Now, it's quite nice that already with 1/4 of the data by 2012, we had surpassed that expectation by a factor of 2. So already we were at 20 MeV or less back then, and now we are discussing 10 MeV. So I think it just goes to show that once we have data, then one can do substantially better with constraining many systematics. And hopefully most of the discussion today will focus on those systematics. So just a few words on one last motivational slide, that there is this Peskin-Takeuchi parameterization of new physics, which is a bit generic. Any contribution that comes through the loops on the Z boson propagator, W boson propagator, photon propagator, that the propagator corrections through loops can be captured in this ST plane, usually with the assumption that U is equal to 0, the third one. But the thing I wanted to mention is that MW and gamma W, the two parameters associated with the W, those are the only ones in the entire set of electroweak measurements that constrain the U parameter. So the reason people say U is usually small is in new physics, S and T would be induced typically by dimension 6 operators, and U is induced by a dimension 8 operator. So if the mass scale of new physics is somewhat high, then you would expect additional suppression for U. But who knows, right? So we want to just make the measurements and see whatever new physics that might illustrate. So I will flash this slide, which is always been shown as a motivational slide in color code, which is to say, given, say, the 2.2 inverse femtobarn measurement from 2012, here were the systematics from then. How would the systematics get better if we quadruple the data? So from 2012, continue the analysis and use the full data set, which would be 4 times larger. So which of these uncertainties are expected to reduce and by how much? So that part of the motivation to continue the analysis on the full data set. So historically, we've tried to make sure that at least the ones that are labeled in green, the idea is that we design the analysis such that all those systematics can be controlled by the collider data completely. So there should be not much reliance on external information, probably possibly zero external information. So that if you could model your data completely, then those systematics could be reduced by the increasing size of the data set. So that's the green ones. The black ones are also data driven, but a little more dependent on exact detector characteristics or things that you could not model perfectly. So that's why the color code is different. And the red ones are even more reliant on external information. As you know, parton distribution functions mostly relying from Hera, other deep inelastic scattering experiments, Drelian experiments, and then some data from CDF and D0, and also a lot of data from the LHC. So maybe some input from the collider, but mostly from outside. And radiative corrections are completely theoretical. So different color code there. So we'll see what happens to this table in the new analysis. So W production at the Tevatron. There are some benefits here, which I think help to contain some of the systematics. Quark-antiquark annihilation producing a W, but always accompanied by soft gluon radiation, sometimes hard gluon radiation. Also, there is some gluon-induced production. So the gluon splits into QQ bar, and then one of those annihilates with the other parton. So the gluon-induced production is somewhat small at the Tevatron. So that's a benefit because gluon-induced production tends to be less well known. Heavy flavor-induced production is also small. So that's another benefit. only about 2% of charm-induced production, 6 or 7% of strange-induced production. So smaller numbers than, for example, LHC. And the X range at which the Tevatron is operating for W production, X parton momentum fraction 0.04 or so. Here, at least one of the quarks or the antiquark from the antiproton is a valence quark. So valence quark distributions are also somewhat better known. So 80% of the time, you're getting at least one valence quark. So that's another benefit. So here is an illustration of how W decays, clearly lepton and neutrino. So neutrino is completely gone, which means if you want to understand the event, you're relying on the measurement of the initial state radiation with the hadronic calorimeter, which is not very precise. And you're relying on measuring the lepton momentum extremely precisely. So lepton momentum calibration achieved here, which we spent some time discussing, is 0.004%. So very, very precise. The hadronic calorimeter, which we call the hadronic recoil, recoiling activity against the W, is much less precise and also much less fundamental in terms of the analysis for it. Much more parametric and just fitting a lot of distributions. But we think that can be nailed down to something like 0.2% calibration. So this combination is able to get the total uncertainty that we are quoting. Okay. So let's go to a quick look at the detectors. The COT yellow region is the central open cell tracker. So I'll keep referring it to the drift chamber as the COT. You see up to rapidity of 1, it gives beautiful coverage. There is essentially no dead regions. It's completely hermetic in a sense up to that rapidity. And so the muons and the electron momenta will be calibrated in the drift chamber. Then the electrons are used to calibrate the electromagnetic calorimeter from the W and Z electrons. So there is some external information, but the final accuracy and final precision all comes from the electrons decaying from the Ws and Zs themselves. And then the rest of the detectors are catching all the soft pions and kaons and photon conversions, I0 to gamma gamma and everything else. All that stuff we call the hadronic recoil. No attempt is made whatsoever to distinguish the components of the hadronic activity. We just want to get one vector out of it, which is the PT of the boson, so to speak. Okay? Muon detectors on the outside. So same thing in a picture. Here you see the drift chamber and the silicon detectors being installed. Okay, so event selection is relatively simple. It turns out the samples from Ws and Zs bosons are relatively clean. So we make some simple requirements, and the usefulness of keeping it simple is any kinematic bias which might affect the PT distribution or the transverse mass distribution, which we are going to fit. If there is a bias, then you have to measure that bias and incorporate it. Otherwise, you get the wrong answer. So you want to minimize that bias. On the other hand, it's also nice to have the misidentification backgrounds, which are really hard to get fundamentally. So very hard to simulate. You have to just play a lot of games with the data, like QCD jet background or pion or kaon decays in flight, things like this. You have to extract purely from data-driven techniques. So to keep those backgrounds minimum is also helpful. The selection hasn't changed. From 2012 to 2022, we have kept the same selection. In the 7 analysis and 2012 analysis, there were improvements, fine-tuning these selections to find the best optimum that we could. But after that, we didn't think there was any further need to make any improvements there. So with this, you will see the total misidentification background from all different sources is about less than 0.5% actually from both the electron channel and the muon channel. So here you see the statistics, roughly 2 million W bosons in each channel. The Z bosons expected fraction just from production cross-section and acceptance. And you will see the significant effect from acceptance in the Z2 electrons relative to Z2 muons. And this is because mainly the CDF calorimeter by construction has a geometry which is made in sectors. So it's like 24 sectors in azimuth. And between the sectors, it's the scintillator, lead scintillator calorimeter and hadronic calorimeters, lead steel. It's scintillator and steel. So the readout of the scintillator and all of that is between the sectors. And so those regions are not good for measuring the electron energy as well. So all those acceptance and fiducial cuts is substantially hurting the acceptance for the electron channel, especially in the Z's compared to the W's. So with this, I mentioned the robustness already. So moving on from there, you will see I will try to illustrate how at least the very important things are measured in multiple ways. And if those multiple ways come out with consistent constraints, then we are able to combine those multiple ways and increase the precision. So we often get the question, some of your precision is substantially better even beyond statistics, for example, compared to D0 or something like this. And quite often the answer is we have not just the Z bosons as a control sample, but we also have this control sample and that control sample. So there are more informations extracted from the data, which is part of the robustness logic, but it also contributes to the precision logic. And the other thing is try to minimize bias wherever possible, including usual blinding strategy. And one thing, as I emphasized earlier, not only are we making blinded measurements of MW, but we also include a similar blinding analysis for the Z mass. So we really want to demonstrate that, for example, the momentum calibration done with J size and epsilons is so, you're so confident about it that we can actually measure MZ, and now with substantial statistical precision, particularly in the muon channel where the momentum is measured. So with this, I'll discuss the alignment of the tracker in a few slides, then discuss the momentum calibration in a few slides, first for the muons and then for the electrons. With this, we are able to demonstrate the Z mass, and you'll see the unblinded numbers that we got a couple of years ago. I will say a few words on resolution, and maybe in the last 5 or to 10 minutes, I will flash a lot of data just to show you how the hadronic calorimeter modeling is done. And there's a lot of these distributions in the paper itself. Okay, so starting with the drift chamber, have to get this right. So this is the aluminum end plate, complete big disc, 1.3 meters in radius. So 2 of these from the 2 ends of the cylinder. So we're looking at the cylinder from the end. The beam pipe is coming in and out of the plane of the paper. And these slots cut into the aluminum end plate shown here is where the cards are installed, and each card has 12 sense wires. So arranged in 8 super layers, a typical particle will cross 96 sense wires. And the efficiencies are about 99.9% for getting a lot of hits on the outer ones. On the inner ones, because of the occupancy, instead of 99.9%, it's something like 99 or something like that percent. So maybe 1% efficiency loss on the inner super layer and really no loss on the outer. So it's a very, very high efficiency drift chamber. So that also is important because you can see any track coming through this chamber. It's a very uniform device. And so the response of the drift chamber after alignment and calibration is a very smooth function. So this analyticity, shall we say, of the drift chamber response is going to be an important argument in saying why we think we can calibrate across the entire momentum scale. So starting with cosmic rays for the alignment. So this technique, I think, was also used at LEP before, that you get a continuous shower of cosmic rays from the sky. Of course, there are dedicated cosmic runs, but those are not what we use here. We are clearly live for muons in the collider running. So when the beam is on and the muon trigger is operating for physics, the duty factor for the muon trigger is about 5 to 10% for cosmic rays as well, because we have a lifetime of about 20 nanoseconds around the beam crossing for the muon trigger. The beam crossing time itself is about 396 nanoseconds. So you can take the ratio and you get 5% or something like this duty factor when any cosmic ray coming during that window is going to fire the same muon trigger, which is firing the W's and the Z's. So because of that, you are sampling the detector in situ, exactly the same conditions as relevant for collider operations. So in 2003, we published this limited author paper designing or a modification of the tracking algorithm. Originally, of course, the tracking algorithm is looking for tracks going out from the beam axis and has a sort of a constraint directed towards the beam axis and also a constraint directed towards the timing. So by modifying all of that, one is able to fit a cosmic ray track across the entire detector, not just from the inside out, but all across, outside in and on the other side. So this kind of a cosmic ray fit is quite powerful for alignment, because any deformation that you can imagine in the drift chamber, twisting, turning, end plates rotate, or because of the tension on the end plates, which is not entirely axial, there is also stereo wires, you get a twisting effect of the end plates and things like this. So those will directly induce track parameter biases on the collider tracks. But because those biases are in one direction at the top and the opposite direction at the bottom, you become very sensitive to those kinds of deformations when you look at the residuals with respect to a complete line from the top to the bottom. And secondly, cosmic rays are roughly equal in number, plus and minus, a little more plus, but you can average them appropriately and get a sample which is on average extremely high momentum. So basically you make the curvature of the sample on average 0. So that gives you an extreme high momentum on average sample with which to do the alignment. So this technique was exploited 3 times. Just before every one of the analysis we have published, there was an attempt to make this better and better. We of course got more cosmic rays as time went on, but more importantly, the techniques of cosmic ray alignment kept getting better, particularly every time there was a non-closure or some systematic bias in the chamber, which was not completely resolved in the, say, the 2004 version or the 2008 version of the alignment. It was again repeated, and roughly a year and a half, every one of those times, a year to year and a half, was invested in just getting the alignment as best as possible. So this final iteration, I encourage you to look at this NIM paper, a lot of plots there. You can see this is against azimuth. So x-axis is azimuth for one particular super layer. This is the innermost radius. You can see the level at which all the residuals are collapsed down to 0 with a statistical precision of roughly 1 micron. And initially, it starts with the survey accuracy, and the mechanical survey has an accuracy roughly 50 microns. So you see a scatter of 50 microns before alignment. But more important than just statistics is how consistent is that across the chamber. So starting with this very simple sanity check, you can do the usual separate track fitting. So one track at the top and one track at the bottom. And there's a small amount of energy loss going through the middle, but correcting for that, you expect the same parameters of the 2 tracks because it's the same particle with just a small change in the momentum in the middle. So the first 5 plots here are the sanity check, where you take the spatial parameters of the fit from the top and the bottom separately, and you compare them. And that comparison, if it's perfectly the same, then you get 0. You can see how uniform, centered on 0, and how Gaussian these distributions are, with very small tails and very little skew, essentially symmetric. And I emphasize this because in the previous iterations, it was not so perfect. There would be, on average, you can make it 0, but it would be some skew on one side or the other. So, something is not quite well understood even after you've done the alignment. The bottom right plot here is the timing. This is T0. So it's the time at which the cosmic ray occurs. So we even constrain the drift model across the chamber in this analysis and show those also in that particular paper. So not just alignment, but improvements of the drift model, getting the nonlinearities in the drift model understood and so on was quite important. So this bias cross-check can be done. So these are the open circles. If you focus on those, it's those average quantities I just showed you, but not only on average, but also as a function of azimuth, also as a function of polar angle. So we looked at all kinds of things like the electrostatic deflection of the wires, the gravitational sag just from the weight of the wires. So many, many things about the entire geometry of the drift chamber was studied in detail. You can find all of those in this paper. So after alignment, it's not just on average, but also as a function of these positions in the drift chamber everywhere. The alignment has collapsed all those biases down to essentially 0. And you can zoom in on these plots here in that particular paper. You can see for comparison how it was before the alignment. Lots of biases and scatter. So with this, we are able to say that the drift chamber is now describable by an analytic response function, which can be considered, for example, in the measured curvature of the track is some parametric function of the true curvature of the track that you are trying to infer. So ideally, this quantity measured would be this polynomial with C2 equal to 0, C0 equal to 0, and C1 equal to 1. So ideally, it would be measured is just equal to true. But there is some remaining biases, and we'll discuss possible sources. The first one is at infinite momentum, you may still have some overall bending like this, which perhaps the cosmic ray analysis did not quite catch. So there you can now take the collider data and say, take the difference between positron and electron, take the calorimeter energy divided by track momentum, this ratio, where the numerator is not dependent on the charge, but the denominator is biased because of the C0 term. The measured curvature is systematically off. But if that is so, then this difference plotted versus, say, polar angle or versus azimuth, that difference will show the bias. And you see at the momentum of the relevant electrons, 35, 40 GeV, this bias, which was initially a small but non-zero, we can basically apply a correction from the collider data and make it zero. So the correction itself is statistically significant, small but statistically significant. But with the statistics of the data, we can make it so insignificant that really we don't want to show the decimals. This C0 term is effectively disappeared from the analysis from this point on. So the next thing we have to do in terms of calibration is get a C1 number and figure out what the C2 is so that we can make a correction and eliminate C2 as well. So finally, we are after the C1, which is the final calibration. So let me quickly flash forward to show you what happens with that, and then I'll come back and discuss the rest. Here. So this plot people look at, of course, we also looked at it for a long, long time. This is the J-psi invariant mass fits done in bins of curvature. So the x-axis is divide the J-psis in bins of curvature. Each of these points, you make a mass fit for the J-psis and you extract a C1 number out of it. This is the C1 number. But if the C2 number is not well controlled, then what ends up here is a line. So it's important that we do the algebra correctly, which is easy to do. If you take that polynomial in curvature and simply do the math and say what would be the invariant mass as a function of curvature, you get a line. The intercept of this line is C1 and the slope of this line is C2. And so you can add a C3 and a C4, but within these statistics, there is no motivation, no improvement in describing this particular plot by adding any more parameters than this. So finally, we are down to C1 and C2. So the C2 parameter is what you can do the analytic calculation and you find that if there is an energy loss experienced by the particles, that will induce a C2. So clearly there is an energy loss, of course, as the particle comes to the detector, but we are modeling that with very high accuracy. It turns out that we have to make a small adjustment to that energy loss, 2.6% of itself. So it's a 10 MeV energy loss. We have to make a 2.6% correction on that 10 MeV, which we think is in the material model. So the passive material is slightly miscalculated by 2.6%. That eliminates the slope of this line, which means that effectively we have incorporated the C2 number within the analysis. So when the fits are repeated, therefore the C2 comes out 0 in the next iteration. After that, the level of this line is the C1 number. So this is the important reason. We get a lot of questions that this momentum scale is not at the same place where the W and Z is, which is over here at high momentum. But even if that, that is true, of course, but given the analyticity of the tracker, this line has to be just a flat line, and you can do a lot of math and there's no way around it. So that's our argument. Okay, so now we come back to the physics modeling, and I'm sure in your workshop you will have, I think, CP and so on, you'll have discussion of Resbos and the Resbos 2. So On that note, I will simply have this one slide mentioning that at the Tevatron, we started this in, it is 7 analysis analyzed. Starting from the 92, 95 analysis, ResBos started getting used. It was an accurate calculation at next to leading log in resummation and next to leading order in perturbative physics or high PT physics. Somewhere within the last few years, it went one higher order, but our experience was that everything we could see from the collider data, ResBos itself was working quite well. But that's an open discussion. Is there any improvement in the ResBos 2 which might affect this analysis? So we'll come back to that point. But for a very long time, we have been able to work with ResBos. And for some reason, for example, the Atlas analysis is not able to find good agreement with ResBos. So that's an open question. Why ResBos works so well at the Tevatron? Even D0 has used ResBos for a long time. So we'll keep that aside for the moment. We are interfacing photos to ResBos to get the photon radiation of the W and lepton and so forth. So let me start with the photos part first. Photos is pretty good for lots of photon radiation, so it's photon showering in some sense, but it doesn't have all the electroweak physics. Maybe later versions of photos have improved, but before that there was already this Horace calculation, which is exact electroweak at one loop. So everything is exact at one loop, and it has some attempt to correct for higher order effects in the multiple photon radiation as well. So the 2 photon, 3 photon amplitude is corrected with the same correction that is extracted at one loop. So they have lots of details in here. So we did a cross calibration of photos to Horace, and that's discussed in this limited author paper. And here you'll see a comparison between the two programs on the energy of the photon there, number of photons on the right-hand side plot. Many, many distributions are shown in this paper. So you can see how well they agree and some small differences. But then you can do pseudo experiments. You can generate Monte Carlo with one program and fit with the other or vice versa. So you can pin down exactly in a very quantitative way if there is any difference that is relevant for W mass or Z mass. So that's included in this 3 MeV systematic. So Horace has, Photos also has a lot of this, and Horace has a little more of the electroweak physics in here. And so those are cross-calibrated out. Okay, now we come to the QCD part. So historically, the ZPT spectrum has always been used. And here you see in the muon channel, ZPT, and electron channel, transverse momentum of the Z. This is done with the leptons. So the resolution is very good. If you completely forgot the resolution and looked at the Monte Carlo with perfect resolution, these histograms would be shifted by about half a bin. So half a bin shift with completely neglecting resolution. So that tells you what the effect of the resolution is on this plot. But of course, we know the resolution substantially higher accuracy than its absolute magnitude. So resolution effects are really small. And you can see the level of agreement after tuning. So historically, it was a 1 parameter tune, mainly on the peak. So ResBos has a non-perturbative parameter. We have a couple of non-perturbative parameters. At some point, we included a second parameter. You can call it alpha S or lambda QCD for fitting the high end of the spectrum in the perturbative region. So every time this 1 or 2 parameter fit has come out consistent with the data itself. So then we end up propagating the statistics of the 2 parameters and their correlation. So it's an open question whether a generator with higher order physics, higher order QCD, would continue to do this well, and whether the differences in the generators are captured by the tuning that we have done here. So I think you will hear from maybe ResBos authors and other people on that. So we think the answer is we have become somewhat generator dependent by being data driven in this manner. Okay. I'll come back to the WPT as well, which is a new feature. One more plot looking at the azimuthal difference between the 2 leptons. So this is like a phi. And this means that as a function of PT, if this variable is 0, it means the leptons are back to back. So this plot is again sensitive to the PT of the lepton. When they are not back to back over here, you have high PT. So historically, we didn't use this quantity, but it's independent of the previous one, because that one is more sensitive to the PT measurement. This one is really only sensitive to the angle measurement. So it's independent parameters of the track. And you see this works quite well. Now we are ready for the momentum calibration. So we have to model, like giant, for example, how are any particle coming through the silicon detector and going through the drift chamber, how it will experience all the physics effects of material interactions, multiple scattering, Bremsstrahlung, Compton scattering of the photons that come out, all kinds of details like this, ionization energy loss, everything. So in some sense, we have recreated all the important aspects of giant. A lot of just read the documentation, read all the papers on all these interactions, and incorporate that into our simulation. So all of these details are provided in our 2014 PRD and the previous one, which is the 2008 PRD. So this is convenient because since it's our own simulation, we can always check those equations. We can change those equations, extract any systematic associated with any detail simply by rerunning the whole simulation with the small change. So here is a high granularity material map of the detector. Just an illustration, for example, of the silicon detector. This is the same geometry incorporated in GEANT. We just extract it out and basically run all those equations ourselves for propagating the particles through this geometry. Okay. Here is another layer of that geometry. So this is silicon at 4 centimeters radius, opened up in azimuth and in Z. And you can see the bulkheads of the 3 silicon barrels and some material in the middle. So this is sort of a heat map, higher density or more aluminum here and less material here. So high granularity. Okay. So with this propagation of particles with their energy loss, Landau distribution for energy loss and all the details, we showed this map. So you get this plot from the bind in momentum and so forth for the J size. So you get one momentum scale from the J size with the line being horizontal with very high precision. Now we can use that for the epsilons. And so here we have the epsilons being measured with an additional constraint on the beam axis. So the track can be constrained to the beam axis, or you can eliminate the beam axis. This is one more check on the alignment of the drift chamber. And in the 2012 paper, if you look carefully, you will see there is a discrepancy here. So there was something we did not understand about the tracker, and that gave us plus minus 12 MeV, a 12 MeV difference between the two. So there was a large systematic uncertainty associated with that. So it became a priority starting the new analysis to figure out what the problem was. And it was figured out what the problem was. So now you see very good consistency. With this correction to the momentum of the tracks from non-beam constraint, you see the width is larger. Epsilons with the beam constraint, the resolution improves. So you see the width is smaller. But you will notice that this number is almost the same. And so we have showed that consistency in the paper. So now we can get a separate momentum scale from the J size and the epsilons, and you find that they're also consistent with each other. So all 3 numbers are consistent. Here is a table of systematic uncertainty. So you should notice this is parts per million. So some of the uncertainties really are down to 1 part per million or a few parts per million. Some of them are maybe of order 10 parts per million. This number here is because of you saw some points on the J-psi plot were not looking so nice on the line. And so you can play some games on those points. And that turns out to be the largest systematic on the J size. And you will notice that on the epsilon table, the largest systematic is actually the epsilon mass is not known to better than 27 parts per million. So when we calibrate on that, this becomes the largest systematic uncertainty in the epsilon column, which is kind of gratifying. We could measure the epsilon mass ourselves and improve the world average is one way of interpreting this. So now we're ready to unblind disease. That was done a couple of years ago, 2019 or so. And this is the number we got. So same number, no change. The analysis was frozen. So you see the nice consistency. So this is an actual measurement of the Z mass. And you can then independently check with LEP. And these are you see it's statistics dominated, everything else is rather small. Okay, this plot was shown, but now we can add the epsilon point, 1 point rather than 5. We actually have 5 or 6 epsilon points here, binned out, but collapsed to 1 for making the plot look nicer. Here is the independent from the Z. So now that the Z is measured, you can add that point and you can see the consistency of all of the momentum analysis in one plot here. So this is the final number applied to the W's, which is the average of all of these points. So now we go to the calorimeter and do with the EM calorimeter similar as much possible first principles analysis. So here again is a separate paper describing in NIM a geometric description of the calorimeter with all the showering. So it's a lead scintillator calorimeter. So a separate geometry was built with all the accuracy, talking to the experts of everything known about the EM calorimeter was built into this particular giant exercise. And then from that, you can get the prediction of the leakage from the back or how much energy lost in the front. All the showering properties can be parameterized from this. So that is what was done. So here you see the electron leakage on a log scale. So the calorimeter is about 18 radiation lengths. Ideally, maybe 20 radiation lengths would have been better. So you wouldn't have this sort of 1% leakage occasionally. So -1 on the log scale means 1%. But a few percent, sorry, 10%. This would be 10% leakage here, 1% leakage here. So you can see, roughly a few percent leakage is happening. We've extracted that as a function of energy of the electron. So these are the gamma distribution like parameterization of the leakage as a function of the electron energy and so forth. So many such parameterizations are extracted because we don't know the geometry exactly. This is then incorporated into the simulation, and now we are ready to predict all the distributions you can measure for electrons. For example, calorimeter energy to track momentum. Here is the actual spectrum of the data, and the simulation is the red line. And this region is the radiative region from Bremsstrahlung. This region is the leakage region where energy in the calorimeter is higher than track moment, is lower than track momentum. You see the resolution described very well from the fit, and the peak is telling you the scale of the calorimeter. So this distribution is used to pin down some details of the detector geometry. And then this fit is done in many different ways. Another way of doing the same fit to tune the radiation model. Another fit of the same is done by binning in the transverse energy. So now you bin in transverse energy for the W's and the Z's. You get each of those calibration points as a function of ET. You can use that to eliminate any small nonlinearity in the showering calorimeter with this beta number here, logarithmic nonlinearity. You can do that as a function of tower rapidity. So this is pseudo rapidity. So this is a uniformity scan. You can do this as a function of time. You can do this as a function of azimuth. So our roughly 2 million W and another 60,000 Z electrons, 100,000 Z electrons. All of those get used to sort of pin down all the different things you can imagine are varying in the EM calorimeter. So both the tracker and the EM calorimeter were done as most principles as we can. So with this, we can use the Z mass as another check. And finally, one more calibration point. So you can see the consistency of MZ measured from CDF compared to the left value. Quite good. So now let's move on. Here is more studies with the Z's. This time we are separating out one radiative electron and one non-radiative electron. So you can see the radiative electron gives you in terms of the track mass. So this is not even the calorimeter. This is directly the track. So this is the radiative track giving you a substantial tail. So this can be simulated and you can get a mass fit from it. So binning in 3 different bins, 2 electrons, both non-radiative or both radiative or a mix. You can see 3 separate Z masses in the calorimeter measurement. So the EM calorimeter is used. Or you can just go to the tracks directly, which is really much poorer because the tracks are radiating. So the resolution is much worse. But you can see within those large statistics here, good consistency. So we think our radiative model is in good shape given the statistics of the Z here. Okay, resolution. Let me just say in interest of time, you saw a lot of peaks. The Z mass peaks and E over P has a nice narrow peak. J size and epsilons, they all have narrow peaks. So all those peaks also are telling you, in addition to calibrations, the resolution of the tracking or the resolution of the calorimeter. So you can pin down the resolution very well from all those peaks also. Small systematic uncertainties from resolutions. Okay, now hadronic recoil. So this is essentially just PT balance. So you know the PT of the leptons from the Z, you can balance that against all this soft activity and just do a detailed parametric calibration of the hadronic recoil. So this is what is done. There is a very important aspect that the energy associated with the muons or the electrons in the calorimeter, that is not part of the hadronic activity. So you have to remove that part. This we've done very detailed, it's important. So for example, if you open up the calorimeter, and these are the calorimeter towers, you can see the average energy in the towers. This 61 MeV is the average from the soft photons and pions and kaons and everything else. This region here, close to the impact of the lepton, clearly the electron impact point is here, the muon impact point is here. Those numbers are the energy depositions by the lepton. And you can see some of that is spilling out. So this region has to be removed so that you don't get any contamination from the lepton energy. When you do that, then of course, this 61 MeV average in all that regions, 7 of those or 3 of those here, is also removed. But that's not supposed to be removed. So you have to correct for that. That's part of the hadronic activity, which is in the event. So you have to put that back in some sense. This particular removed energy has to be calibrated very precisely. And that is shown again, measured from the data, again, against the simulation. So the simulation is incorporating all of this behavior. These are just kinematic quantities. So we have measured how that hadronic energy depends on the kinematics of the event and incorporated that into the simulation. Okay. With this, we are able to get the rest of the calorimeter energy now calibrated. So this is the response of the hadronic activity. The fact that response is low here is mostly because most of the soft particles don't even reach the calorimeter. So clearly, so soft pions and soft kaons are not reaching the calorimeter, so you don't even see them. At high PT, the response is now limited by the HCal intrinsic response, the cracks, various regions where you don't get good response. So it goes asymptotes to something like 70%. These are the axes in the Z's, the PT axis and the perpendicular axis. These are the axes in the W's. There is only the lepton axis and the perpendicular to that. So we'll make a lot of projection plots against these two axes. And from now on, I can just flash in about 10 seconds each. The response, average value, or the width, resolution, so forth. So we can just look at the quality of the agreement. So this is a resolution plot. This is also a resolution plot, the width of the distribution versus PT. The width of the azimuthal resolution. So this is PT of the boson and the hadronic recoil from the leptons, from the hadronic activity should be back to back in azimuth. So 0 would be back to back. So you see there is a lot of resolution there. These plots are low PT. Lower plots are higher PT. So at higher PT, it becomes narrower. Only thing we are looking at is the red histograms, which are simulation, are describing the data. And I would say it's worth noting the level of detail here would be much more than the 2012 paper, and certainly the 2007 paper. So more plots, low PT, high PT, and you can see the quality of agreement. Many more plots in the paper. So those were the Z plots. Now we go to the Ws. Few more plots on the Ws. Just looking at the quality of agreement. And finally, this is the WPT. So this comes back to our Resbos argument that now we are not just constraining to the ZPT, but you might say there is a degree of freedom from going from ZPT to W. And rather than relying on the generator to completely predict the W, which is how it was done in the past, we are now looking at the WPT spectrum also. So this is x-axis is PT spectrum of the W measured from the hadronic calorimeter. So a lot of resolution effects here. But You can make your simulation on top of that, and you can vary the simulation. You can vary the WPT while keeping the ZPT fixed. So you might imagine some QCD scale dependence, higher order physics, whatever. So that got studied by another program, and we incorporated that as an additional constraint. So we now have both ZPT and WPT as constraints. Okay, I think I can finish in a few minutes now. This, of course, is another long topic. So there is a significant discussion on the paper on this. A few points I will just mention quickly. Historically, we were using next to leading order PDFs. So we tried those again just for old time's sake and find good consistency. But we have moved on to the next to leading order fits of the PDFs, which are the three groups mentioned here. They give consistent results on our fit. We have chosen NNPDF for the central value, but you can see probably wouldn't matter much which one we used. The uncertainty extracted from NNPDF is, for us, easier to understand how to present that. So that is why we have chosen NNPDF. It's the central value and the uncertainty. Okay. We even looked at higher order effects in the PDF fits and so forth, and those are quite negligible. Okay, we can come back to this. And finally, the backgrounds, maybe 1 or 2 slides on backgrounds. Down here are the misidentification backgrounds, but you see on the next slide, those are data-driven, but actually quite small. The largest one is Z bosons with a missing lepton. Most of this is acceptance. A little bit of it is efficiency, but we can measure that efficiency very well. And the nice thing is the trigger for the Z bosons is actually the same as the trigger for the W bosons. It's a single lepton trigger. So you get a nice control sample where the second lepton is reconstructed offline, and it goes into various uninstrumented regions or poorly instrumented regions. So you can literally map out the lepton acceptance using tag and probe, standard tag and probe. Okay. With this, you will quickly flash a table of systematics. You'll see sometimes some large systematic, but mostly few MEV on most of these. So this is the background's contribution. Okay. Now I can, blinding stat is pretty standard. Some random offset is chosen, and at some day you remove the random offset and keep the analysis essentially the same after that. So 3 different fits, transverse mass. I would just look at the bottom plot, which is the difference of data minus simulation for the best fit. So if the distribution has to be well described, otherwise you can't trust the answer. So you can see it's relatively flat. We can go to lepton PT and pretty good fit. We can go to the worst of the lot, which is the neutrino, which is completely inferred. So hadronic activity and lepton together is neutrino. Pretty uniform residuals, no pattern there. So these are the other, more robustness sort of demonstrations. 2 channels and individual fits, which have different systematics from hadronic recoil and backgrounds. You noticed different contributions in each of these. So their consistency is quite good. And if you look at a roll paper, in fact, the consistency was not as good as it is now. So various aspects of the analysis have improved. The consistency can be quantified by just combining different fits and different channels. So you can see out of the 6 channels, combining various combinations, the chi-square column tells you, taking all the correlations into account, how good is the agreement between the different fits. Then you can do separate electron and muon channel and the combination from all 6. Okay, so here's well-known number, but you can see whatever you do with the different fits, you are getting the same unusual number, shall we say. So this plot, this table was slashed, and now I can play this game of just flipping back and forth to see the improvement from the old analysis to the new analysis. Improvement meaning improvement in precision. Okay, so one more maybe, and we can finish up. Okay. More details here, more systematic tables on the combined answer, and we can also look at, for example, improvement in the lepton energy scale from 7 MeV to 3 MeV, mostly statistics, but also fixing that important problem. Okay, so with this, I think I'm ready to finish. This plot is in the paper, and this table is also in the paper, and I'm sure there's a lot of discussion of other measurements and differences between measurements, so we can discuss that in question and answer. Okay. There is a couple of slides here and many more in the backup. So I've posted the slides, you can download them. A lot of improvements over the 2012 analysis, and if there is time, we can discuss impact of those improvements. But here's the bottom line. You see the numbers, and so the paper ends on this note. We do not quote p-values. I think it's well known, systematics-driven analyses, p-values are not meaningful. But just to get a sense of the level of difference from the standard model, you can do the numbers in 2 minutes and see nominally it's 7 sigma. So we'll see what this means. Analysis improvements, we have some possibly in mind, improvements, extensions to the standard model, other people are thinking about. So on that note, let me thank you for your attention, and yeah, good, finishing on time. And I hope we can spend time on questions. For me, it's the morning, so I'm quite available. Thank you very much.
Thank you very much for the detailed explanation. Other questions or comments?
I have one question. Hello, I'm Song. Can you hear me?
Yes, perfectly.
Okay, I'll turn on my video. So, but would you go back to your slide about D0? Yeah, here. No, next one. So, do you have any combined analysis with D0? Because you have the same machine, right?
Yes. So in 2013 and in 2004, each time, first from run 1 and the measurements from run 2 we had up to 2012. Those were combined and published as separate physical review D articles. Mm-hmm. So there are 2 physical review D articles combining CDF and D0 from the past. We are making the same attempt now. So, this paper came out 2 months ago. So now we are discussing with D0 how we can do combination again. Maybe, let's say 1 year from now or something like this, we will have that paper. The combination paper, of course, has to be approved by both experiments. So the usual review has to happen within CDF and within D0. So let's say 1 year from now, it should be available. Yes, indeed. So in that discussion, we will, of course, now have combination issues like we have now a different parton distribution function for the central value compared to D0. So D0 would have to make an update of their parton distribution function input. So this will take them some time. They are working on it. After those things, we will see what other inputs should be the same. Correlations should be relatively easy. I mean, part of your question is, what about Atlas and so forth? So that is a much more difficult question. People from CDF, D0, and Atlas have been actually trying to pin down correlations between Tevatron and LHC, and that is turning out to be quite difficult. Really, almost 3 years have passed on those kinds of studies, and there the issues are the generator level issues are very different. We are using ResBos-like calculation, resummation, and all of this. Atlas has done a very different type of generator study with very different inputs. Their parton distribution function is also very different. So many things there are much more complicated. And 3 years have gone and we still don't have correlations completely understood. So the idea was to publish those correlations as well. Hopefully that will happen at some point.
Okay, thank you.
That is telling us LHC versus Tevatron is another non-trivial physics level thing. And that may also take some more time. D0 combination should be faster.
Okay. I'm looking forward to it. Yes. Yeah, very good. Yeah.
Hello, do you have enough manpower at the moment to combine the D0 and the CDF result?
Combination
It's not very.
Within Tevatron alone we have done it twice. So in a sense, it's a better idea of knowing what it would involve. So tentatively, I think we have a feeling that D0 will be able to update their old number to the new parton distribution function.
I see.
And mostly that is the main one. The rest of the correlations, in principle, we can use even the old studies and basically proceed with the correlation coefficients we had in the past. So even if the actual systematics have changed for us, not for D0, the correlation should be the same. So we might be able to make that argument. You have to think about it carefully, and you're just new to this now, because this analysis just came out. But I think we can make the right arguments and get that one without too much additional manpower.
Okay.
The large manpower, I mean, number of people are thinking about the LHC versus Tevatron correlation, and their significant manpower is going. And so that's a much longer conversation. The other thing about D0 is we are wondering now, D0 I think is making a statement that perhaps the analysis they did in 2012, which is the final analysis, that analysis used half of their data. D0 measurement is 4.3 inverse femtobarns, roughly half of the total. But mostly it should be maybe some, perhaps Anki from D0, but I think there is some statement that others have already made from the audience. So I can maybe repeat what I have heard, that some radiation damage has happened and perhaps the second half of the data is not analyzable. So my personal hope would have been that we can get more D0 analysis also done. It's interesting, right, this number. So we'll see from the Tevatron if another measurement could be made. Perhaps no more result from D0 will come. Let's see. So now the combination with D0 is just a combination exercise, not additional analysis exercise.
Okay, I see.
Maybe. Let's, you never know the future, right?
Anyway, I wish to congratulate you on this
Thank you.
really impressive improvement.
Appreciate it.
CDF one data. And I'm not sure if this is a proper question to you, but how well do Atlas and CMS can improve this their uncertainties? Eventually, I mean.
Eventually. So let me tell you what I can say. For the last 10 years, I mean, everybody knows I am an Atlas collaborator, but my involvement in the electroweak precision part of Atlas is 0. So in 2012, I made a decision that because I was interested in continuing this CDF analysis with the rest of the data, I was going to completely detach from the Atlas precision physics program. So you have to be independent, right? I mean, whatever these numbers are, it is crucial that the rest of the world see independent analysis. And so you don't want to be hearing details and discussing. And I say this in public now. We don't want to make the same mistakes. Everybody has some systematic this, here, there, you make some decisions. But the worst thing you can do is make the same mistakes. So this is why my understanding of the Atlas analysis is only since this paper was submitted and all gone, then becomes fair to read the Atlas analysis very carefully, read their paper very carefully, do comparisons and look at differences. We wrote down for ourselves literally a 7 or 8 page detailed comparison of how we do this systematic, how Atlas is doing this systematic, how D0 CDF does this, how Atlas does this. Long thing. And there are many, many, many differences. Some of them have to do with production model at LHC is substantially more complicated. More heavy flavor, more gluon induced, W plus and W minus is not the same at LHC. It is the same at Tevatron. So this induces many, many additional things which Atlas has attempted, which we do not have to bother with. Then on the experimental side, our emphasis on the tracker from all the J size, epsilons, alignment, there is much less of this discussed in the Atlas paper, but maybe future Atlas, future CMS is going to do this. So the systematics associated with the momentum calibration is a very different approach. It is completely based on the Z and Z alone. So you can do a lot of things with the Z's because much more statistics with the Z's. But it is, I would also say the following, that the Z is an invariant mass. So you have three-dimensional momentum that you are using. For the W, you only have transverse. So it is not exactly the same three components, the 3 components versus 2 components. So there is a bit of a feeling in my mind that when you calibrate on 3 components and then you pick out one of them and get the 2, it's not exactly the same. You can see there is a assumption or something has been done. So they have done all that. They have looked at the polar angle and tried to get a systematic from that. And for us, it's a much smaller effect. So this conversation can go on for a long time. I'm recalling our 10-page comparison of this analysis versus Atlas, for example, and many, many, many differences like this. So one way I would think is if some of the techniques we have used could be used at the LHC, then you get substantially more precision by using other data set, not only Z. But if you continue on the Z alone, it's somewhat of a different game. And I don't know where it gets limited. But in principle, statistics become infinite. So in the end, I can also say that our expectation of how CDF or D0 could do based on long ago, statistics were expected. But what you can do when you have the data to analyze is often much better than what you think before you have the data. So this argument goes in the sense of, let's say we'll keep having more and more data and new analysis techniques get developed. And so systematics can be improved that way. So I think it will depend on how much effort goes into thinking of all the possible questions of the systematics and how many different analyses can be done to control all those systematics. But my personal feeling is if something could be done to go beyond just a Z boson based analysis, it would be better.
Thank you.
While waiting for another question, I would say that about 6 years ago, CMS in public did show a plot like our JSI plot, doing JSI fits in bins of curvature and the same plot that eventually that plot looks horizontal. They showed that plot, I believe, at the LHC committee. But since then, that plot has not been shown in public. So that plot disappeared now. It's not flashed anymore in any workshop. So I'm not a CMS member. Maybe you can ask internally. So we know the difficulties. So those plots, making them consistent involves, you can wonder why, we were taking 5 to 6 years for the first 2 analyses. This time it took almost 10 years. As the statistics improve, those plots become harder and harder to understand with the precision you want. So time also is required.
So this number will be the final number from CDF.
Yes. So
Okay.
I have posted the slides. So there are many backup slides. You can see many things we changed. At this point, and that was the other reason, we wanted to make all the improvements we could think of. And because there won't be any new data, unlike in the past, when you could say, you can always think of improvements, 6 months before you are ready to submit the paper, you think of some improvement. But of course, by that logic, you are never able to submit. You can just keep making improvements forever. But in the past, you could say, all right, there's a next analysis, and we can incorporate whatever we think of again and again. Now the data is finished, so this motivation is gone. So we waited to make all possible improvements. But of course, the time passes and you get some more ideas, and somebody will say, how about a different generator, better generator? So the only thing that is left is if the community from all this ResBOS 2 discussion, which will happen, say, in the next year, already we are planning a workshop with many colleagues, maybe at Fermilab, maybe somewhere, to discuss generators and things like this. If there is a consensus that, yeah, maybe there is some, I don't know, 5 MeV effect, which we can pin down by fixing the generator better. The study, so even after, already, from the ResBOS authors, there is a preprint from 2 weeks ago where they talked to us and they said, how do you do the analysis? We will try to emulate it. So they did a reasonable job at emulating, and they published a comparison of ResBOS versus ResBOS 2. You probably will hear from them in your workshop. And if you look at table 2 of their paper, their conclusion is maybe it's a 1 to 2 MeV effect by updating to ResBOS 2. So, which we feel was a good decision. We may have spent 1 year to update to ResBOS 2 in the middle, because then we have to calibrate and validate the whole generator, which a lot of investment from the past we have to redo. So we feel like probably was the right thing to do, to not take another year or whatever and update to ResBOS 2 ourselves, because the effect turns out to be small. But maybe there is another effect, maybe this, maybe that. So if in the end of the day, a year from now or something, we realize that maybe there is an update of 5 MeV or something, 7 MeV, I don't know, little larger than a few MeV. It might make sense that we literally spend the effort and make that update and produce an updated number. Our expectation is it's maybe a 5 MeV update, maybe smaller. But at some point, you have to judge whether it's worth it. There are other ways to make a couple of MeV change, but in the big picture, it doesn't change anything. So the answer, I think, to your question is there is no plan. This is our final number, but we reserve the capability to make an update.
Okay, thank you.
Which hopefully encourages people with other generators. So we have heard from people who have interfaced MCFM. MCFM is another next to leading order generator. It has been interfaced to another resummation program. And so they also have a ResBOS-like package now. It is not an event generator. It is a calculator of cross sections, and that's all they have. So that's why we could not use it. But they have directly asked me, if we were to turn our program into a generator, could you use it? So we can do a comparison of that program versus ResBOS. If there is a significant effect, we'll figure out what it is. Maybe that is a reason for an update, for example. So most updates are all coming down to some update on the theoretical modeling. We don't anticipate any other analysis change. There's no other idea on our side. there is an Italian group as well. They have yet another resummation program now called Radish. So maybe somebody will try that one and we can compare also. So I sent a message. These slides are on the web. So feel free to please copy them to your page or whatever. Within any institute in the world, this is open science. I mean, my first thought is that the paper itself in Science is completely open. It is open access. So last week I was just looking at it and there were 150,000 downloads or something. Clearly there are not 150,000 physicists. Certainly not particle physicists, right? 10,000 particle physicists. So another 140,000 people from wherever are downloading. So the paper itself is completely open and everything here is in the paper. So I'll check with somebody, but it seems to me this is open science. Good question. I've never been asked that in 30 years. Suppose historically, every seminar was always in person. So whoever was in the audience is there and whoever is not in the audience is not there. So who knows? So this is the first time, I guess, that's the other reason. This is the first time this question has come up is because everything is on video. So yeah, I will find out. Yeah, interesting new world.
That's right.
Yeah, maybe it's a good thing to be public because people should be finding out about particle physics. It's good for particle physics to be understood or known to everybody.
So if there is no more question, maybe we can close the session.
Okay, happy to.
Yeah, thank you very much for your sparing your time and giving a very nice presentation of your work.
Very good.
Thank you very much.
It is just the last word. I think your June 24th workshop will be very interesting. I'm going to be in India for a family visit.
I see.
Even that would have been okay. I could do Zoom from India. It turns out exactly on that day I'm flying from New Delhi to Mumbai. So I felt like it would be dangerous to promise. You know, something happens, the flight gets delayed. Now, you know, trying to do Zoom from the airport would be horrible. So let's not take that risk. So good luck with your workshop. I'm curious to see what you will learn and discuss.
Yes. Thank you very much. Yeah.
Okay. Thank you.
Thank you very much.
Bye.
Thank you.